SIOS asked me to talk about storage, SQL Server, high availability, and what you can do basically outside of a SAN, because we've all kind of been conditioned to think about SANs as kind of the high availability storage platform for SQL Server. And I don't necessarily agree with that. So what I want to talk about today is we'll start off with kind of a brief history of storage, how we got to where we are, what a SAN actually provides us in terms of storage cluster protection, what are some of the other elements of SAN storage, where SQL and SAN simply don't get along, where those assumptions and design compromises just clash with each other rather badly, and what I think is the best of both worlds, a SAN-less cluster, where we can get high performance, high availability, and no single point of failure. Before we get started into the presentation, though, I'd like to ask a quick poll question. Greg, if you put that up for me, please, on what storage are you using for SQL right now? Are you using a SAN? Are you using, let's see, okay, here we go. Are you, sorry, my screen seems to flash. Are you using the SAN? Are you using local storage, flash? Are you using rotating media? What exactly are you using here? Wow, that's some pretty serious numbers right now. If you're looking at, I'm looking at the real-time results here. Almost all of you, 85, 90% approximately, are using SAN of some type. Only 1% is actually using local flash storage. That's surprising given the number of Tier 1 applications out there. Let's give this another, okay, give it another about 15 seconds or so. Give it a full minute for the poll, and I think we'll be good. Wow, so most folks are using a SAN environment. All right, Greg, let's just call that closed, and we'll put the slide back up. 88% SAN. That's serious. Good. Well, let's talk about how we got to where we are today. Storage really comes with two different characteristics. Either it's persistent or it's transient. It's either sequential or random. And storage is simply the data that data processing processes. Ever since we've had some type of computing device, it's had to be able to take input and record answers. We started off with things like punch cards and tape, paper, magnetic. These were examples of persistent sequential storage. Eventually we got to random storage, core storage, drum storage, disk storage, and now we have flash. Personally, from an aesthetic standpoint, I like core storage. If anybody's ever seen a picture of a core storage unit, it's almost a work of art. There's actually people have had segments taken out and framed. Anyway, a little side one there. And of course, our transient storage, we started off with physical relays, and now we have actual RAM. There we go. And I was on the wrong slide. Okay, let's talk about a focus on our persistent random storage. The picture you see is actually from 1973. It's an IBM 3340 Winchester, so-called model hard drive. The drive, I believe, the unit you're seeing, the dual units, are approximately 4 feet tall, if I remember correctly. Retailed at $87,000, almost a third of a million, or a little over a third of $1,000,000 in today's time. But the real numbers that we need to care about are not the size or the capacity. It's those last two numbers that you see. 35 millisecond seek time. And in rotating media, the seek time is simply the time that the head that reads the track moves to the correct position and settles in and is able to start transferring data. The second number is how much data we can transfer at one time. Let's just make it easy on ourselves and round that off to 1 megabyte per second for reference purposes. Well, let's compare that to what's available today in persistent random storage on an individual drive basis. On the Seagate Savio high-performance drive, that's 300 gigabytes. That's roughly 1,000 times what we had before, 4 orders of magnitude. $400 retail just for the drive, and a 3.3 millisecond seek. So while our capacity has gone up by 4 orders of magnitude on the high end, our seek has only gone up by 1, and our sustained transfer rate has gone up by maybe 2.5 orders of magnitude. If you look at the high capacity drive, the numbers are even worse. At 3 terabytes, we get the 5 orders of magnitude, but our performance is really, really down. 8.5 millisecond seek, barely a quarter of what the original commercial drive had, and the sustained transfer rate's about the same as the other drive, still about an order of magnitude and a half. So we've got this massive imbalance in terms of how much data we can store in our persistent storage and how fast we can get it in and out. And that's only been getting worse as compute power and memory capacity has gone up roughly in accordance with the storage capacity. So we've got a big bottleneck there. One thing that makes this bottleneck worse is the fact that we're calling it random storage in the idea that I can access any particular cell, unit, block, or whatever you want to call the unit of storage on the device without regards to which device or which block was there before, which block I just read. But I really can't, because there's a big difference in performance. This is why I call this pseudo-random storage. The analogy I like to use on this is really a hotel elevator. You can think of the elevator itself as the disk head, whereas the tracks and the disk correspond to the various floors of the hotel. And then you have the rooms. You have to actually go out to the individual rooms. Rooms that are further away from the disk or from the elevator actually take a lot longer to get to. And what this ends up is actually a differential in the cost of our I/O operations. We have random and sequential operations that come up with an absolute difference in cost. The ratio has stayed remarkably consistent since the beginning of rotating media, and it's about a 5-to-1. So I can do 5 times the volume in a sequential I/O, in terms of either number of I/O operations or the amount of data, either one, versus random I/O. And anybody that's ever used an elevator in a hotel understands all of this almost instinctively. There are times that the elevator itself gets full. There are times that, depending on what floor you're on, it's going to take a long time and how much traffic is between you and the other, how many people want to get off at different floors before you end up with the getting to go where you want to go. Even though you may be the first person in the elevator and you start off on the ground floor and want to go to the top, you don't necessarily get there. The elevator kind of optimizes things for you. Strangely enough, the disk does the exact same thing, totally internally. The other differential is, of course, reading versus writing. A read is a read. You just pull the block off the disk, and it's done. But when you write, you actually have to do a read plus a write plus a read to verify that it actually made it onto the disk correctly. Now, we've talked a lot about, so far, just about individual disks. When we start putting them together, this is where we start getting things like JBODs, just a box of disks. We get RAID arrays, and then we get up to the true SANs. And the SANs all share certain attributes. First of all, they're almost all disk-based. They were designed around disk bases. If anybody's ever tried to purchase solid-state media for SAN, you realize it is insanely expensive. And what you're really buying is not so much the solid-state disk. You're buying the software changes in the SAN to implement all of that, because the SANs are really designed to optimize and minimize those rotating media issues that we just discussed. Second, a SAN generally has a fairly large amount of cache, at least relatively compared to, say, just disk arrays. The biggest piece, though, is the abstractions. Everything in a SAN is abstracted. You don't ever see, unless you're the SAN administrator, what the underlying storage actually is. You just see a logical disk of arbitrary size. It may actually have real blocks underneath it. It may be thin provision. We'll discuss that in a moment. The whole purpose of these abstractions is to consolidate. Rather than having a physical disk of a particular size that I may only use 10% of, you actually consolidate all of those spare resources into a great big pool and allocate them as necessary, either as a manual expansion of a LUN or automatically by provisioning, by having a large LUN provisioned thinly and having the SAN actually create or apply the storage as it's necessary. And this is pretty common. One thing you can look at real quick is any of you with laptop computers or desktop computers, look at how much free space is on your boot drive. If it's anything over about 120 gig or so. I checked my mother's this weekend. She hasn't even cracked 50 gig, and she's got 300 plus. So instead of paying for a lot of extra storage scattered around, one of the ideas of the SAN was to consolidate all this. Now, performance, in theory, a SAN is going to perform better because of large stripe size, kind of like RAID on steroids. Internally, it uses the different RAID levels that we've come to all know and despise, or love, depending on which ones they give us. But it uses very large stripe and block sizes, almost like it's trying to read an entire cylinder or track at one time, trying to minimize basically aggregate all the little bitty IOs into one big IO. Now, from a SQL and high availability perspective, the big thing we like about a SAN is it unlocks clustering. We can finally have a disk that is shared, or at least connected to multiple systems, and use that as our redundant and highly available repository, even though it is somewhat of a single point of failure in itself. But we can unlock clustering, and now we get away from the host failures and can rapidly and automatically use Windows Server failover clustering and SQL clustering to make sure we have a highly available and disaster resilient system. Now, I mentioned RAID very briefly, so I've got about 18 slides real quick that we're going to go over all the different RAID levels and what they mean and how they work, or not. Y'all have seen I'm sure y'all have seen all the different diagrams and pictures, even the funny water bottle cooler pictures. Google those. Go Google or Bing those if you haven't seen them, on what the different RAID levels mean. But all we really care about right now is the compromises that RAID provides for us. Do you want cheap? Do you want fast? Do you want fault tolerant? Pick any two of those, just like a software design project, and you can have that. And that's the level of detail that we really need to go into for RAID for this. As far as SANs themselves, there's really two major designs. There's kind of the monolithic SAN. This is where they mostly started. Single controller head, usually a redundant controller head, operating a failover mode. There's a lot of drives hanging off those controllers, but it's still one physical logical unit. If you want more capacity, you buy more drive trays, plug them in. At a certain point, there's an upper limit to how many of these things have. This is a very common design. The EMC CX series uses this a lot. The other one is what I call a brick SAN. This is more like the compellent or left-hand SANs, where they take basically a commodity server and build bricks, use those as your bricks, where they have a controller and the disk in combination, or controller and a number of disks in combination, I should say. And then we RAID the units as well as the individual disks within them to provide the redundancy that you would see in a failover monolithic type SAN. From our perspective, these don't really show up a whole lot of difference. They all run under similar assumptions. They all operate with the same type of abstractions. The brick SANs tend to be a little heavier on the internal I/O because they're having to move data around between the units rather than internal to the unit. But for our intents and purposes, they're pretty much the same. SAN has a certain number of assumptions, though, that are built into the way they're designed and operated and really should be used. More importantly, SAN administrators are trained that this is the reality of storage. The first one is that all I/O operations are equal. But we know, based on what we talked about a little bit ago about physical disks, that I/O operations are not equal. Random and sequential have very different performance. Random and sequential have very different performance operations. Now, for non-SQL workloads, this works just fine. I mean, SANs were originally designed to be either file servers or consolidated OS storage units for virtualization and other consolidation technologies, or they were used for like maybe great big media servers. And so the patterns that they optimize for fit all of these not SQL workloads. large stripes to reduce the I/O operations. Well, that's really great when you're doing file services or media services, because you're basically opening a file, reading all the way through it, and then stopping one time. You're not jumping around in the middle of the file like, oh, I don't know, maybe a database server. Data can be compressed and deduplicated without slowing performance. That's a fairly modern one, because most SANs are finally been built with enough computing capacity to do the deduplication and compression. But that does take time, especially if you overfill your cache or run out of cache. Again, OS, because you have a lot of copies of the same OS, you can deduplicate performance with there. SQL data simply doesn't deduplicate, and generally the effort to do so costs you performance. Everything is one giant resource pool. That's not a bad idea. I mean, if we can use the storage effectively. But the final one is something that really kind of grates on me, and that thin provisioning doesn't matter. Real quick, thin provisioning is when I represent an abstract that has a certain amount of storage, say 10 terabytes, but it only allocates a physical block of storage when I write to that block. It just puts a counter or a marker for empty blocks. That gets to be a problem, because unless you're the only thing using the SAN and you're only adding to the end of the logical data that you have, you really have absolutely no sequential I/O anymore. As I slowly allocate blocks by adding data into the system, it grabs the block from the next available free resource pool, and that may be several blocks away. So it may show me a logical sequence of blocks, 10, 11, 12, 13, but those are random on the disk. And again, the SAN people say that it doesn't matter. I say that it really does. Let's look at how SQL works on these workloads. All I/O operation, no. In SQL, we know that sequential I/O is faster than random I/O. Otherwise, why would we bother defragmenting indexes? We defragment them because our scans, which are necessary parts of certain queries, will operate faster. So when we start getting into these large scans, the SAN doesn't work as well, especially if we've written that data in a random order, because at that point it definitely won't be on the sequential order that we've tried to put it back into inside of SQL. The large stripes, you're actually having the SAN start trying to manage cache when you do all those assumptions. SQL, if you're going to have cache, you really need to have the cache up in the SQL server, especially the read cache, because SQL will manage it more effectively. It uses the least recently used algorithm to decide what blocks it needs to keep and what blocks it can reuse. On the flip side, a SAN needs to actually have a fairly large amount of write cache, because SQL will batch writes. We have the lazy writer that kind of trickles it out in the background, but we have that checkpoint process that comes along every now and then and synchronizes our data transaction log, or our transaction log with our data file. So we have to have the SAN able to absorb that quickly and use the cache to spread that out over time. Typically, we have randomly written blocks, whereas the OS images, the media files, and even non-media files are typically written sequentially, more like a data warehouse workload. But when you randomly write it and then sequentially read it, you're essentially randomly reading it when you get to a SAN, so you're losing 80% of your performance. We can take these assumptions that are built into the SAN and the way the I/O patterns work with SQL and really make a SAN administrator miserable. Try this sometime, but don't do it on your production box, and don't tell them I told you how to do this. Create a very large file. Now, this file needs to be a significant multiple, at least 5 or 10 times the size of the cache in the SAN, because you want to overdrive that cache. You want to begin a sequential read and read just large enough to trigger the read ahead in the SAN. Then write one small block within that read ahead area. This will dirty that whole big stripe. And so the SAN now has to go back and put that back on the disks, causing even more overhead. And of course, with the RAID stripe that most SANs are going to do, they're going to tell you RAID 5, and you're going to like it, and you're just going to deal with it. Well, this is going to be the least efficient in terms of performance. And then skip ahead somewhere. go to the middle of the disk, middle of whatever LUN that they've assigned you, which hopefully will correspond to the middle of the disk, especially if you remember to take this large file and completely fill it with data. So you actually have physically allocated storage. It's not thin provisioned anymore. Read again, trigger your read ahead, write a block, and repeat this thing. You will thrash the SAN into oblivion. I had a friend of mine take a top-of-the-line SAN, I'm not going to mention the name, and specifically target based on the read-ahead triggers, the cache sizes, and everything else, and eventually bring the whole thing to a grinding halt. This wouldn't be so bad, except this actually looks like a fairly typical, maybe extreme, SQL Server workload. So when you see things like that, the SANs don't get along with SQL Server, largely because we have different goals. The SAN goals are designed to consolidate storage and lower the price per megabyte, gigabyte, terabyte, or whatever of storage capacity. But as we saw at the very beginning, storage capacity is the metric that we have the most of, the resource that we have the most of. What we really need is I/O capacity, the ability to load data in and retrieve it quickly as possible. So SANs have issues with predictability because the resource pool is allocated on a demand basis underneath, and the resource, again, that we're tuning for is I/O capacity. It grants that to whoever demands it the loudest. The abstractions take away our sequential I/O advantage that SQL spends a fair amount of time tuning. We give away a lot of overhead for large stripes, especially when we're doing small transactional reads and writes. There's another piece in here, work queue aggregation. This is something that I actually have seen in a production environment before. It's called in to troubleshoot a cluster crash. And they couldn't see anything wrong with the cluster itself, and to be fair, there wasn't anything wrong with the cluster. What had happened was the enterprise in question, and this was a very large enterprise, had a very large SAN, and the standard was to take all 15 drives in a tray and make one single RAID set out of it. And then they sliced that into 100 gigabyte LUNs and handed those out and thought that was just as ideal as they could be and they were going to be super efficient. Well, what happened is they stitched about, I think, between 12 and 15 of those LUNs together to create a large enough file for, or large enough logical storage unit to create a large database file for a data warehouse. And when this ran the ETL process, every one of those individual LUNs had its own work queue. Remember we talked earlier about the elevator and how the elevator is going to basically hit each floor in order. Well, disks do the same thing. And it's the work queue that allows that. It remembers what floors are requests or what buttons are pushed, what blocks are needed. But each of these LUNs had an individual one, but we all know those are simply abstracted representations. There's actually one great big physical work queue inside. And because each of these could contribute a certain amount, that work queue had a very large aggregation. The total amount of work to do was tremendous. And as we've seen in Data Warehouse, when you get an ETL system cranking really, really well, you can load a lot of data very, very quickly. And what happened was the single little request for the cluster disk to go, hey, are you alive, got lost down in that work queue. It didn't really get lost. It just got behind a very long line. And the line was so long and the queue length was so bad that it actually timed out the cluster disk. And if the cluster disk doesn't respond in a certain amount of time, it thinks it's offline, crashing the cluster, forcing a failover. So the work queue aggregation is something, especially when you have thinly sliced SANs, that you absolutely have to work for or watch for. The scary part is, unless you're the SAN administrator, you're not going to have visibility into that very much. And then what I described on the previous slide was kind of an example of resonance. We're triggering read ahead and the optimization to go in one direction, and then we're pulling in the other one immediately. And we keep that up back and forth, back and forth. Ultimately, it ends up thrashing the SAN, and all it's doing is loading cache that you never use and then throwing it away. So ultimately, this is largely the fault of SAN administrators. They're trained to get the most out of these very expensive devices, And by their standards, they're doing a great job because they're being very efficient in storage use. But as database professionals, our job is to deliver predictable performance to our end users. They have to know that when they hit the button on the web app, the back end is going to respond within a guaranteed time frame to meet our service level agreements. So how do we make this work? Well, basically, don't use a SAN. Be your own storage administrator. Control your abstractions. Bring them all up to one layer where you can see the resources in comparison with each other. And use dedicated resources. If you're sharing a SAN with everybody and their brother, somebody else can put a workload on it that you don't control. Also, shape your storage for your workload. Pick your RAID property, or pick your RAID type carefully based on random versus sequential I/O. Try to reduce the RAID overhead. We always want the fast. They always want the cheap. And again, it's usually the person that's actually controlling the storage that gets to make the choices there. Finally, properly tune your cache. Put the read cache in SQL, put the write cache either in a SAN or whatever storage device that you choose. One of my personal favorites as a way to build this is using a SANless cluster. One of the problems with local storage is I don't have a high availability or a disaster resilient story with it. But if we use DataKeeper Cluster Edition, it helps you build a SAN without having, helps you build a cluster without a SAN. It uses block replication, and it represents the resulting storage piece as a clustered storage resource. Just like the SAN shows up in your cluster, you can build any clustered workload on top of it without having to actually have a SAN or deal with the SAN administrator. It's really the best of both worlds. You get to tune your workload. You can use tiered storage in this. You can combine rotating and flash so that you have fast storage for the really, really critical current data, and maybe rotating for some archive or image storage. SQL read cache, but you put all that up in the system. There's really no shared resources. You control it because the storage that you're using is inside your SQL server, using the network to communicate and synchronize everything. You can still abstract it, but it's fairly minimal. It's enough abstraction to be useful, but it's not enough to hide the resource consumption, and that's where I find problems with abstraction. By the time you get to see storage, it's so abstracted that the metrics that you're using to try and measure are pretty meaningless. And of course, it's highly available and disaster resilient. Easy to use. Set up and maintain it very simply. Uses an MMC snap-in to control it. Completely integrated with the Windows Server failover clustering. You can even do this in Azure and Amazon. You overcome a lot of the limitations of always-on availability groups, including the requirement of Enterprise Edition. You can actually do this with Standard Edition if all you need is 2 clustered nodes. And you can use this with a combination hybrid mode where you have one system on-premise and one system up in either Azure or Amazon. And so you can use that to migrate your cloud or migrate into public cloud without having to take large downtimes or rebuild systems from scratch. We can even go multi-site with this. There's no restriction that these have to be together in the same location. The only catch with that is if you're going to do multi-site with Standard Edition, you have to stretch your network subnet across there. So anyway, I hope it's been helpful to you guys, you people, folks, about a little bit about where we came from with storage and SANs and why SANs maybe aren't the best answer in terms of storage for SQL Server. Greg, I think I skipped over the second poll question here. Let's go ahead and ask that one right now. There we go. So is a lack of an inexpensive failover protection a barrier to SQL in the cloud for you? Also, if you have any other questions, please feel free to pop them up in the chat system, and we'll take a look at them and see if we have some answers for you on this. Okay, I'm wondering how many of the no votes are because it's not a barrier or because you're just not planning to go to the cloud yet. But it's about 30. Okay, okay, Greg, I think we can, well, let's keep it going because we haven't had a lot of votes yet. Okay, there we go. It's running about 2 to 1 no at this point. But again, I think a lot, I would suspect a lot of that is because people just do not have a, we got to migrate to the cloud strategy yet. We'll talk about that maybe in a future discussion. All right, I think we're pretty good. Let's go ahead and we've had a minute and a half. Let's go ahead and close out the poll and open. Are there any questions from the audience, chats, etc.? Questions here. Oh, can I elaborate on my comments about standard edition and high availability? When the last feature reorg happened with Microsoft SQL Server, clustering was added to the standard edition SKU, but it was limited to 1 subnet and 2 nodes. So you can still use standard edition SQL. You'll have to use, and now with Windows Server 2012, there is no enterprise edition of Windows. You would use standard edition Windows, which enables clustering, standard edition SQL Server, which also enables clustering, and DataKeeper Cluster Edition, which would be your storage replication and abstraction piece. Hopefully that's that covers what you need. It seriously works. Let's see a question here. When you test your SAN, are you using SQL IO? That's one of the tests I use. I'll sometimes use SQL IO. Sometimes I'll drop back to going and using IOmeter or Iometer, or however you want to pronounce that particular toy. I like that one a little bit more because I have a lot more control over it. Now, here's a tip when you're going to test your SAN or any storage for performance. Do not rely on the metrics out of the performance tool. Use the metrics from Performance Monitor built into Windows. And the reason that you want to use those particular metrics are because that's what you're going to have available to you during the database system operation. So that way you're not worrying if there's any kind of regression to the mean with aggregated numbers or anything. You're going to be getting absolute an absolute parity because you're using the exact same tool to measure before and after. I've seen folks trying to use some of those metrics coming out of the tools versus metrics in Performance Monitor, and they don't get good comparisons. This way, your before and after look exactly the same. SIOS software solutions fully compatible with VMware. David, you want to go ahead and take that one for me real quick? I'm pretty sure I know the answer, but we're bringing in David Birmingham from SIOS. He's their technical expert. He's a clustering MVP, and he's actually a little better at the guts of this stuff than I am. David.
Yeah, thanks, Jeff. Yeah, absolutely. The solution Jeff was talking about, DataKeeper Cluster Edition, runs on Windows operating system. So regardless of the hypervisor platform or cloud platform, the software is going to run inside the virtual machine to allow you to build the SANless cluster that Jeff was describing.
Mm-hmm. Yeah. You would be clustering at this point as the 2 guest machines, not necessarily at the host VMware ESX layer. Now, the one thing I would recommend is if you do build a guest cluster, you need to do something called anti-affinitizing those 2 guests. The 2 guest machines should not land on the same host at the same time. And if you set anti-affinity for that, it will attempt, as long as you have enough resources to put them somewhere, to try and keep them from failing over onto the same host at the same time.
Hey, Jeff, I got some questions here. Maybe I'd like to grab one if you want to look at some of the other ones while I'm answering this question. This one is specifically around, there's a few people asking about AWS support and some people are asking about whether trial software is available. We at SIOS, we can certainly get you trial software, get you up and running in a test environment. This one specific question about AWS was, do your SQL clustered servers have to be on the same subnet, same availability zone in AWS, or can I have them in different ones for HA? So the answer to that question is you certainly want to have your SQL servers in different availability zones in AWS. That's going to provide you protection should an availability zone have a failure. By being in different availability zones, that's going to require that your nodes are in different subnets. So you will be deploying clusters that are cross-subnet. So you're going to need the SQL Server 2012 Enterprise Edition or SQL Server 2014 Enterprise Edition for that cross-subnet failover in the AWS environment.
Okay. Yeah, I got a question here. We looked into the DataKeeper, but lack of material experiences, customer stories. So they went with the traditional SAN server. Well, let's talk about both SIOS and DataKeeper. SIOS has been in business for better than 10 years, and the DataKeeper product has been around for quite some time. It's a mature product. I've had a lot of success with it, and if you like, on the last page we have some follow-up. Here's how to contact us. We have a lot of good customer stories and a lot of good experience that they're willing to share with you on this. It's a rapidly growing customer base that is very happy, especially when you do things like local flash storage. One of the things that we've seen a lot of people use in SQL Server in the last year or two has been things like Fusion I/O cards and solid-state storage that's not just disks but is actually PCI-based storage. And that's a great performance boost for SQL Server, but it comes with a cost of there's no high availability storage because it's back to local storage. When you combine DataKeeper with local flash storage, it's really a multiplier effect. You get the benefit of storage of flash-based storage, either standard SSDs or with the PCI-based storage, with the high availability of a traditional cluster. And we actually ran some metrics on this, and it's about a 10% overhead. When you compare that to the always-on availability group's solution, which is about an 80% overhead. So really, if you're going to go with local flash solid-state storage, then giving away 80% of that performance just to get high availability, you're kind of back where you were with the SAN to begin with. But with SIOS and high-performance local flash storage, you get the best of everything in there. And we've had some customers that I was really concerned that we were going to be able to keep up, even with throwing 20 or 30 or 40 drives underneath their particular solution. But with the solid state devices and DataKeeper, we were able to give them the performance levels they wanted at a much lower cost point. All right, let's see. We have any? I think that. All right, I think we've kind of covered all of the questions out there. David, do you see any that we've missed? Oh,
no, I mean there are a few questions that are like, what RAID configuration is the best? We could probably have a whole hour session answering that question.
I got one here I got one here on any suggestions for good books for SAN administration for SQL DBAs. Get the heavy one. That way, when you hit the SAN administrator with it, he'll listen to you.
There's some questions about your comment on standard edition, high availability. So just to be clear,
I talked about that one. I already answered. I covered that one a little bit, I think.
Okay. Yeah. The cross-subnet failover issue is an issue when you're using the Microsoft failover clustering. The SQL Server team wants to squeeze as much money out of you as possible, so they limited that ability to fail across subnet to SQL Server 2012 or 2014 Enterprise Edition. So even though the Standard Edition will support a 2-node cluster, it only supports a 2-node cluster in the same subnet.
Right.
SIOS does have another solution that's a cluster alternative to Microsoft Cluster Server, which will allow you to do cross-subnet failover using all versions of SQL Server. So that is another option. And that's called the SIOS Protection Suite.
Yeah. Got one question here. He's trying to do a sanity check for new SAN that's presented to the DBAs. And what I would do is establish a baseline on performance. Run SQL I/O, run I/O meter with various patterns that simulate the workload you think is going to be on there, and run it as hard as you can so you know what the maximum capability is. When you're measuring memory usage, you know how much memory is in the box. When you know CPU, there's a handy scale of 0 to 100. Every disk has a capacity in terms of megabytes, gigabytes, terabytes printed on the side of it. The one thing they don't tell you is how many I/O cycles it supports. You need to know that so that when you watch the performance of the system in production, you know whether that number of I/Os that it's consuming represents 10, 20, or 80% of the capacity of the storage system underneath it. Because if it represents 10% or 20%, you're going to be happy. If it's representing 80%, then you need to be talking about how you can increase that capacity. I've always said that if I tell my boss that you need a new server next week, I look like an idiot. If I tell him you need a new one next year, I look like a genius.
So Jeff, another question came in about using availability groups in the cloud, since we're saying that you're going to need the Enterprise Edition anyway. Why not just use SQL Server always-on availability groups? So answer that question, Jeff. You could chime in a little bit. But
Sure, absolutely. The reason is AGs are not exactly 100% the same functionality as failover clustered instances. With availability groups, you have to manage things that are not in the database, like jobs, linked servers, logins. All of that has to be managed outside of the database. The failover unit is a group of databases, not the server instance. Also, there's the performance issues that we talked about a little bit ago. So it's not that AGs are a drop-in replacement for failover clustering. Sometimes you need certain things in a cluster that you're not going to get in availability groups. And so they're complementary to each other, but they're not necessarily 100% replacements. From an administrative standpoint, a cluster is far easier to administer, assuming that you've actually built it correctly and there's no hidden gotchas inside, than availability groups. There's a lot more moving parts involved with availability groups. Demo, let's see here. Let's see, here's one. Nope, we already answered that one. Admins. Okay, I think we've pretty much covered all the questions. Greg or David, you guys got anything else we need to Greg, you think you were going to do the wrap up for all this stuff? Yeah, we'll just wrap it up. And if there's any other questions we didn't get to, we can kind of go through these again, and either Dave or Jeff can get to the individual directly. But I want to thank Jeff for all that great information, and thanks Dave for answering some of those questions. Also want to thank SIOS for sponsoring today's event. So please take some time after today's webcast to visit their site, us.sios.com, to learn about all their SQL Server HA solutions. This webcast was recorded, and you'll receive a follow-up email with links to view the archive. Also get a copy of the slides from Jeff, and you can download those as well. Also, please visit mssqltips.com. You can access all of our free SQL Server resources out there. There's some tips about clustering and past webcasts that you can look at as well. I want to thank everybody for attending today, and when you exit the webcast, please take some time to fill out the survey to
the feedback helps both with today's webcast as well as future events. Once again, thanks for attending and hope you all have a great day.